Hello, now we are going to look at some rules for indices or powers. So our indices or our powers, if we look at our number up here, we have 5 to the power of 3. So the 3 is the indice, and we call 5, the big number, the base number. And it's important we know that base number name as well. So the big number, the larger numbers here are base numbers, and then the powers can also be called indices or exponents. And the rules that we need for these are on page 21 in our formula tables, in our log tables. But it's important that we understand why these rules work so that we can actually apply them, because trying to read them out of our book without understanding them becomes very difficult. So let's have a look at the very beginnings of our powers or our indices. If we have 3 to the power of 2, what does that mean? It means we have 3 multiplied by itself 2 times. So our power, our exponent, tells us how many times we're multiplying this base number by itself. So we're multiplying 3 by itself 2 times. And you end up with 9. Well, here we have 2 to the power of 3 multiplied by, brackets for our multiply, 2 to the power of 2. Well, this means I have 2 multiplied by itself 3 times, multiplied by 2 multiplied by itself 2 times. So it can be useful to say how many 2's have I got multiplied together in total. Well, I have 2 by 2 by 2. That's the 2 to the power of 3, 2 cubed. And 2 by 2 is my 2 squared. So I have the first 3 of them multiplied together. And I have the second 2 multiplied together. How many 2's do I have multiplied together in total? Well, I have 5 2's multiplied together. 1, 2, 3, 4, 5. Well, I had 2 to the power of 3 and 2 to the power of 2 multiplied together, and I ended up with 2 to the power of 5. It looks an awful lot like, if I look at the expanded version of this, I effectively just added up the powers of the first and the second. So this ends up being the same as 2 to the power of 3 plus 2. So I end up with 2 to the power of 5. So in general, if I have 2 to the power of, well, it would work for any number. So we could say any number to the power of 5 times the same number, or to the power of 3, would be x to the power of 5 plus 3, x to the power of 8 in total. So we'd have 5 x's multiplied together, 3 x's multiplied together. In total, we'd have 8 x's multiplied together. And this is the first rule that we have written here. We have the same base number, just like we had x's here and we had 2's here. So we have the same base number, and when we multiply them, we're able to add the powers to see how many of them we've got multiplied together in total. Well, if we have division instead, if we write this out the long way, if 4 to the power of 3 divided by 4 to the power of 2, you can be asked to give your answer for these as powers. So I could have written my final answer as 2 to the power of 5, or I could write down what that is. And you end up with 32. Now, continuing, we have 4 to the power of 3 divided by 4 to the power of 2. Well, that means I have 4 multiplied by itself 3 times, all over 4 multiplied by itself 2 times. But I know that if I have any number divided by itself, it's just 1. So I can see here, this is essentially the same as 4 divided by 4 times 4 divided by 4 times 4 over 1. There's effectively a 1 under here. So this divides out to 1, this divides out to 1, and I'm just left with 4 to the power of 1. Well, that ended up looking an awful lot like I had 4 to the power of 3 minus 2. I had my 2 4's on the bottom divided out. Effectively, the powers ended up looking like they were being subtracted. I'm subtracting this bottom line's power away from the top line's power if I have the same base number. Again, this only works because I'm dividing 4 by 4 and 4 by 4 to end up with 1 in both cases. So this only works with the same base number. But I can see then in general that I would have something like x to the power of 9 divided by x to the power of 3, well, that would just be 9x's multiplied together, or divided by 3x's multiplied together. And the x's on the bottom are just going to cancel out 3 of the power on the top, so it's the same as x to the power of 9 minus 3 is x to the power of 6. I'd end up with 6x's multiplied together in practice. And that is our second rule that we can see here. If we have the same bases, again, you know where this rule is coming from, that we're dividing a number by itself to give 1, so we have to have the same base numbers for this to be true, for this to work. Now, if we have 2 to the power of 3 in brackets to the power of 2, so 2 cubed to be squared, well, what would that mean? We know what squared means, just like we did when we had 3 squared up here. It means whatever is inside that bracket gets multiplied by itself. It does not matter how complicated this bracket is, squaring something will always mean multiply something by itself 2 times. So now we have 2 to the power of 3 multiplied by 2 to the power of 3. Well, I can think here and write that out. I'd have 3 2's multiplied together times 3 2's multiplied together. In total, I'd end up with 6 2's multiplied together. Well, what did it look like I ended up doing? It was like I multiplied these two numbers together. 3 by 2 is 6. So if I have a power on the bracket, I effectively just end up multiplying the powers. That ended up being the same as 3 multiplied by 2. Give me 2 to the power of 6. And that is our rule here. So when you have power in a bracket, we end up multiplying the powers, and you can see why here. If we have it squared, it just means we have 2 of whatever the power is inside here. So we end up having 2 of these, which is the same as multiplying by 2. So we can write that out in general. We had x to the power of 4, so some number to the power of 4 cubed, or to the power of 3. That means I'd have 3 of these multiplied together. So in total, I would have 12 x's multiplied together. I'd have 4 and 4 and 4 x's multiplied together. So in total, I'd have 12 x's multiplied together. Now for the next rules, it is possibly helpful to look at this as a pattern. So if we take this pattern here, 3 cubed, 3 squared, 3 to the 1, 3 to the 0, 3 to the minus 1, 3 to the minus 2. And I would work out the ones that are fairly easy for me to figure out. 3 cubed is 27, 3 squared is 9, 3 to the power of 1 is 3. Well, what's getting me from one number to the next in this pattern? Well, I can see I am dividing by 3 each time. That's the pattern of what's going on. So what happens if I continue that pattern? Well, dividing by 3 again, 3 divided by 3 would just leave me with 1. So this is why 3 to the 0, or any number to the power of 0, ends up being 1. But we can go further. If we keep this pattern going, because we're decreasing the powers each time, so we went 1 and then 0, and now 1 less would be minus 1. So if we have 1 and we divide it by 3, we end up with 1 divided by 3 is the same as 1/3. So that's 3 to the minus 1 is 1/3. And what happens if we divide by 3 again? Well, that would be 1/3 of 1/3 would be 1/9. Or as I'm going to write it, 1 all over 3 squared. So 1/9 is the same as 1 all over 3 squared. 3 squared is 9, so 1 all over 3 squared is 1/9. So what we can see is any number to the power of 0, because you could do this with any list of powers of a number. You could do it with 2 or 10 or 15, it doesn't matter. This pattern will always hold. You would have the number to the power of 0 will always give you 1. And then when you start going into negative powers, when we keep dropping the powers down, we end up with changing the line that the number is on. So 3 to the minus 1 ends up being the same as 1 all over 3. It's like we brought it underneath the line, changed the line that it was on, and we changed the sign of the power. Or 3 to the power of minus 2, well, effectively it's like we move it underneath the line and we end up with a positive power again. That's not logically what's happening, but it is a pattern that is very useful for figuring out problems. And hopefully this pattern will help us see why that is happening, why we are ending up with anything to the power of 0 is 1, and negative powers change the line that we are on. And that is our two rules over here. Any number to the power of 0 must give us 1, and any number to a negative power, we move it underneath the line. And we've seen our argument for why that should be the case, or an argument for why that should be the case there. Now continuing into some examples, we have 4 to the power of 2 divided by 5 to the power of 3, all cubed to the power of 3. Well, that means I have 3 of these multiplied together. And I know what that's going to do. I'm effectively going to multiply these powers by 3. But we can see why that is by writing it out the long way. And you could write it out the very long way. So you would have 4 by 4 by 4 by 4 by 4 by 4. So in total we would have 6 4s. And similarly with the 15 we would end up with 9, with the 5s, we would end up with 9 5s multiplied together. But we can write this out using our rule. This is 4, and we're going to multiply the power by 3, and 5, and we're going to multiply the 3 by 3. So we end up with 4 to the power of 6 all over 5 to the power of 9. And you could leave the answer like that. At a lot of the time they will ask for answers like that. You can also put that in your calculator to find out what the numbers are. Now let's have a look here where we're now having to combine even more of our rules together. So we have 2 to the power of, 2 multiplied by 3 to the minus 2. Well, these are different numbers, just like we couldn't subtract these powers here because these were not the same base numbers. We can't do anything with these because this is a base 2 and this is a base 3. So I have to deal with my power business as best as I can. So I have 2 multiplied by 3 to the minus 2 would be 1 all over 3 squared. Because these numbers are fairly small, I'm going to multiply them out. So I end up with 2 on 1/9. Well, that's really just 2 over 1. So I end up with 2 all over 9 as my answer. And I can't go any further than that because they're not the same base number. Now here we have more complicated business because we have several terms going on. So I see I have 2 base 5s. So I have 5 squared multiplied by 5 to the 4 multiplied by 3 to the 4. So the simplification I can make here is I could have this as 3 to the power of 4 times 5 to the power of 6. I have 6 5s multiplied together in total. So I have 3 to the power of 4 multiplied by 5 power of 2 plus 4. I effectively end up adding up how many 5s I've multiplied together. And here I have 2's multiplied together, but I have lots of complicated powers going on, so I'm going to have to deal with this step by step. So this power of 2 here means I have this multiplied by itself 2 times. The power is only on that bracket. So I end up with 3 on 2 to the 5 on 2 to the minus 3 by 2. I end up with 3, 2 to the 5, 2 to the minus 6. Now I could bring this underneath the line, or I could recognize that as I'm multiplying the same base numbers, I can add the powers. And I end up with 3 to the 2, 5 minus 6, 3 by 2 to the minus 1. So I end up with 3 all over 2, or doing that in 2 steps. Now here I have 4 to the power of 3 squared, and I have 4 to the power of 1 times 4 to the power of 5. And this ends up being 4 to the 6 all over 4 to the 6. Well, that's one number divided by itself. That's just 1. All of those 4s would divide out to just 1. And then finally, I have to have 2 to the 1 multiplied by 2 to the 3, and I can simplify here this by itself. And carefully stepping through each rule one after the other, we're able to simplify things down to our final fraction. And that's what we need for now.